So this is only one, mostly important, but all the pattern, let's say a geometry in the device, right? The geometrical dimensions, all of those will be affected by the roughness because when you do the lithography. But the L is mostly critical, right? Because that will affect the current and the threshold voltage. So those are the static variations. Now we are going to talk about the temporal variation. So the first one is the random telegraph noise, RTN. So this is a temporal effect due to the trapping and detrapping of the electrons into the gate traps or defects. So this is when you have, let's say, the current flowing, let's say electrons flow from the source to the drain, and in the oxide here, the oxide may not be perfect. There are some defects of the oxide, especially when you apply a gate voltage for a long time, you may generate some defects of the oxide. So those defects will act as a trap for the electron. So that means the electrons, when they travel to here, sometimes it will be captured by the trap, and then it will stay in the oxide for a while, and later, due to the thermal vibration, the electrons may be released back to the channel. So that means if you have a constant drain voltage, you measure the drain current as a function of time, then the drain current will have this kind of fluctuation, ID versus time, at a fixed VGS and VDS. Then the current will be something like this. And of course, sometimes you see even more noisy behavior if you have many traps. But because the device dimension is so small these days, probably only one or two traps will be dominant there. So if you only have one trap, then you only see the two levels of the current fluctuation, because when you only have one trap, then you only have one of these trapping and detrapping behaviors. You only see two levels of the current. So this is measure the drain current. Of course, you can translate that as a constant drain current. Then you measure the voltage of the VDS. If you apply the constant current source, you can measure the difference of the voltage, and then you can translate that as sigma of the VTH. So this is some measurement data shows in this kind of behavior. And then this is statistics. So as we shrink the technology, initially due to this is purely due to the RTN, and you see that initially most of the devices will have very small, maybe 10 millivolts sigma. But as we shrink the device to here, then we have a long tail, and some devices may have like 6 millivolts sigma in the VTH due to the RTN effect.
As you said, why there might be multiple traps? That's just one gate and one trap.
The trap is very small. Like for example, typical trap is a vacancy of the oxide. Let's say one oxygen atom is missing, so it's pretty small, and you have let's say 20 nanometer. Of course, you may lose like one or two oxygen atom. Then you can have one or two traps. So this is the RTN, and the other one is this so-called MBTI. This is mostly for the PMOS transistor, because PMOS transistor will apply negative voltage to the gate, so it's negative bias, temperature instability. And of course, for the NMOS transistor, you may have the PBTI, but that effect is much less than the MBTI. So this is a well-known reliability problem. So this is a long-time effect. So the RTN is more like a short-term kind of temporal fluctuation. But the MBTI is a long-term problem. That means over months or years, the VTH will gradually shift over time. And the general trend, I think, the VTH will increase for the PMOS. I mean, the absolute value will increase. So here, typically, people just measure the this kind of MBTI at higher temperature and at higher voltage to accelerate this kind of reliability testing, because you don't want to wait for months or years to observe this. So you have to accelerate this effect by using higher temperature, for example, higher temperature and larger voltage. So this is again due to the generation of those traps at the oxide interface between the oxide and the channel. So when you apply the voltage to the gate for a long time, it's like a stress to the gate, and then it may knock out some atoms, some oxygen atoms, and then you may generate a trap at the interface. And those traps will capture some electrons, and then your threshold voltage will change. So later we will see the flash transistor. You intentionally trap those electrons, and then you make VTH shift and use that as a flash memory. But this one is not your intention. You don't want this to happen. So this is for logic transistor or SRAM transistor. Then you don't want this VTH shift. Okay, so
why does it become long-term versus short-term going from PMOS to NMOS?
No. So here, I mean, the RTN happened for both NMOS and PMOS, and this is more like a short-term. It's not short-term effect, but I mean the time scale you see here, the time like maybe every seconds or even tens of milliseconds, you will see the change of the VTH. And then for the BTI, no matter MBTI or PPTI, those are for the long term. You have to measure that. If you don't accelerate this, you have to observe this after maybe months or years. So this is long-term effect. Of course, here we show second. This is because we accelerate this testing at high temperature and increase the gate voltage to 2.1 volts. So in normal applications, you don't use this kind of stress condition. So this is the gradual effect. Okay, so if you consider all of those effects, and then what you can measure is the sigma of the threshold voltage, and then you can look at different device dimensions, different technology nodes, and you can plot this sigma VTH as a function of the 1 over square root of the area. And then we can have this kind of plot, and this is sometimes called the Pegron plot. And then it follows this trend. This is due to the random this random dopant fluctuation. And then this random dopant fluctuation, as we discussed before, is this kind of model. And then, of course, the sigma proportional to this 1 over square root of this L times W, which is area. And then at a very small scale, so this is 1 over area, so this side is actually smaller area. So you see an increase of the sigma of the threshold voltage. This is due to other sources like the LER or other sources, other mechanisms. And as we discussed, there are different sources for the sigma. And because they are independent, so you can add the sigma squared like this due to different sources. Each source you have a sigma, and you square that and you add them together, and that will give you a total sigma of the device. Any questions? So the variability is key challenge in today's circuit design, not only for the memory but also for the logic and other circuitry. And we will discuss later, like a FinFET, and actually that will help with this problem. But before that, we have a small section on the soft error. So let's look at this first. So soft error is a problem that basically says that the data you stored on the memory cell will temporarily, let's say, flipped and become an error. But it's not hard error. That means you can correct it. If you rewrite your data back in to your memory cell, then you can correct the data. It's not like the cell is stuck at 0 or stuck at 1. It's just temporal flip from 1 to 0 or 0 to 1. It's not stuck at the 0 or 1. If you stuck, then it's called hard error. So the soft error mechanism, mostly are the two kinds of mechanism. One is due to the decay of some of the isotopes. There are some unstable isotopes. You know, any material will have isotopes. So then, for example, in your package, if you have your package, then in the package there are some isotopes decay. Once they decay, it will release the like alpha array. So that is like a radiation. And of course, another important mechanism is the cosmic ray. And this is pure radiation from the universe, from the space. And then even we can, let's say, you know, our atmosphere will shield most of them, but still there are some particles or high energy particles from the space that can hit your devices. So let's say the alpha particles, like the alpha particle is a helium ion basically, and those are from the isotopes. You can shield that, but the cosmic ray, like the neutrons or the heavy ions from the space, cannot be shielded because they have very high energy. From the package, it can go through your package and hit your substrate of the silicon. And then this is more problematic than the alpha particle, so we will mostly focus on the heavy ion or the cosmic neutrons. So the problem is that when you have this kind of high energy particle hit the transistor, so here, especially at the junction area, you know, it's a PN junction. And PN junction, you know, is this PN junction, PN junction. So if you have a high energy particle hit this junction, so the high energy particle will transfer the energy to your silicon substrate. And then if the energy is not enough, it will generate the electron and hole pair. So basically you kick the electron from the valence band to the conduction band, and then you create electron and create a hole in the in the valence band. So if you create electron and hole pair, and then because it's PN junction, so you know electrons will fall off the barrier and holes will pop up. So basically you separate the electron and hole and you generate a current. So essentially this is what happened when you have the radiation effect in your circuits. So the high energy particles hit your PN junction and create electron and hole pair, and then the electron and holes are separated due to the internal built-in electric field in the PN junction. So then you create the current. And this may, if this happens, for example, in the SRAM cell, then it may flip the states from 1 to 0 or 0 to 1. And this is called an upset. So if you have this flipping due to this particle strike then it's called the upset. This is not permanent failure, and it's just a 1 to 0 or 0 to 1 flipping, and you can recover this by rewrite.
But you would have to have the data stored somewhere else to be able to write it back to the cell.
This is all done by ECC, error correction code. Yeah.
So how often does this kind of error happen? It's like when you take your cell phone outside and exposed to the sun, it will happen?
Yeah, it will happen. Yeah, it will happen. Yeah, it will happen. So how often there's there's a flux. I don't recall the number. There's a flux, the rate, but it's quite often actually. But we have ECC, so you don't see that. And also, I would say for commercial product, it's not that critical because we have the ECC, and you can error correction. Even if this happens, then it will be corrected. And this is more important when you talk about the aerospace applications. When you have the when you have the electronics on your airplane or satellite, it's a different story. They don't have the shielding of the atmosphere, then this is much more worse. But even here, you will have that. Not that often, but still it's there.
Are you going to teach the ECC?
No. That is more for computer architecture system kind of courses. So what happened to the SRAM cell if you have a strike? As we discussed, it actually generates the electron and hole pair, and it's like a current. So what you can model this is to inject a Lewis current to the storage node, for example here. And then it will become the same story as we have before. This is like a Lewis current to the SRAM cell. So then you inject current to this node. Then you may flip the state. And then you can run the spice simulation with the current source. And you can look at the trajectory of the SRAM's two nodes, two voltages. You can look at the trajectory. If the noise, let's say amplitude or the duration is small, then you may have the recovery, right? This is the transient simulation in terms of the voltage of those two nodes. If the noise only appear for this period, then after that, then this cell can recover. But if the noise is too long or the amplitude is too large, then we will have this flipping. So this is similar as we discussed the noise. So you treat this radiation effect as a noise current. So what matters is the critical charge you need to dump into the node, or you need to discharge from the storage node. So that will determine the error. And if you look at the soft error rate for the SRAM, and at the cell level, so here first the figure shows not first figure. Let's say this one is the soft error rate of the SRAM cell at the cell level with the scaling. So here when you scale, the SER maintains with the scaling. So the reason is that here, when you scale the technology node, then the capacitance to this node will reduce. And the charge you store there is capacitance times the voltage of this node. So this is the critical charge that you may need to flip the state. So when you scale the technology node, then the capacitance reduce, and the critical charge also reduce, then it may be easier to flip. But on the other hand, as you scale the technology, then let's say this pin junction area, the junction area also shrink. The junction area is the collection area for the ion strike, right? So only when the ion strike on your pin junction, then we may create this electron hole pair. If the ion strike on your other, let's say the insulator or other metal, then it will not cause a problem. So this pin junction area also shrink when you scale. So both the critical charge scale and the pin junction area scale. So at the cell level, the SRAM's soft error rate almost maintains as you scale. But at the system level, because as you scale, then on the same chip area you have more cells. Each cell will have the same probability to flip, but now you have more cells. Then at the system level, then the soft error rate will go up. So simply because you have more cells, and each cell will have the same probability, then as a system, then you will have larger error rate. So that's a problem for SRAM. And on the other side, for the DRAM, the situation is a little bit different. The DRAM, we typically don't talk about the soft error for the DRAM because it's much less concern for the DRAM. The reason is that for the DRAM, as you scale the technology and the sensitive area, the collection area scale similarly. Let's say those transistor size scale, the pin junction area scale. However, for the DRAM CS cell capacitor does not scale. Okay, we will talk about this later when we talk about the DRAM lectures. So, but the DRAM, the critical thing here is the capacitor in the DRAM 1 transistor 1 capacitor. That capacitor's capacitance does not scale. So that means at a smaller technology node, relatively you have larger capacitance of the DRAM. That means relatively you can hold more charges on the DRAM capacitor compared to the charges generated by the electron hole pair generation due to the strike. So the DRAM cell level, the soft error rate decreases, and at the system level, of course, you have more DRAM cells. So then roughly the error rate is a constant. So that means DRAM is not less vulnerable to this soft error. So we don't talk about the soft error for DRAM mostly. Okay, so then I just want to briefly discuss this multi-bit error. So in the SRAM, this is a problem. That means when you have one strike to one SRAM cell, it may cause multiple bits to flip. So this is a little bit strange, but you can understand this through this example. So for example, here we have two SRAM cells, and the data pattern we store here is 1, and this one is 1. And this cosmic ray just hit this location, pin junction here. So if we draw those transistors in this cross-section view, and this is this node here, and here this node is here. Okay, so what happened here is, for example, this cosmic ray hit this pin junction of this transistor here. So we create this electron hole pair, and here the electrons will be collected to the drain of this transistor, because this stores 1, right? So this 1 is high potential, and electrons like to go to higher potential. So electrons will be sink to this node. But the holes, where are the holes go? That's a question. Holes, positive charge, they want to go to lower potential. So what is the lower potential in this circuit? The body, right? So then the body will have a body contact somewhere, P plus. This is body contact, and body contact is always grounded, right? So then this hole try to find this terminal to ground, or let's say sink to that ground. But then in the circuit, then the body contact is not everywhere. You only in one region, you only have one body contact. So that means the holes needs to travel through the, let's say, along the substrate, which is p-type, and then go through here, and then eventually go to the body contact, which is ground. So when the electrons travel through the substrate has resistance, right? So current flow and the resistance of your substrate, this is like a resistor. So you build up voltage along the substrate, and that means the substrate at this moment, this location, is not zero, and the substrate here is zero. This is GND. But since you have current flow this direction, this point is not zero. This is some positive voltage. So if your substrate is positively biased at this location, then here you will have this parasitic BJT, bipolar junction transistor BJT, because here you have, for your all the source and the drain is N plus doping, and if your substrate is P-type, so this is the NPN BJT, and the problem is if the substrate is positively biased, then BJT is turned on. If the BJT is turned on, then here we are going to discharge this one, previous this one here, which is this node. This one will be discharged through this BJT. So then here not only this one becomes 1 to 0, and also this cell becomes 1 to 0. And this may happen for quite a few cells. So this is a so-called a match-up effect as well. So I know this is a bit complicated, but the key point here is that for the normal operation, you never positively bias your substrate, right? That's why the body contact is always ground, because you don't want the substrate, because it's p-type. So you don't want the p-type substrate to be positively biased for normal operations, for any circuits, due to this reason. So that's why you want your substrate to be ground. But in this case, because you are generating the current, and then you have current flow in the substrate, and then the substrate at some locations will be positively biased, then you turn on this parasitic BJT, and you cause the match-up effect. So any questions? Okay, so then the multi-bit error may increase with the scaling, simply because each cell is smaller, and then that whole current may travel longer to go to the ground, and then you may cause multiple bits to flip.